All right, so when's y'all's test in here? Over 4-1 to 4-4? Tuesday, good. Tuesday, not Monday. Tuesday. We're gonna take an extra day. Not Sunday. No. Sunday's the big monster truck jam, right? Sunday, Sunday, Sunday. It's either the big monster truck jam or the big mattress sale. They use the same voiceover. Sunday, Sunday, Sunday. All right. These two warm-ups are basically in the same vein. If you have a base that is between 0 and 1 and an argument that is greater than 1 or vice versa, right? You know that your answer or the log itself is going to be what type of number? Yeah, I think so. It's going to be what? It's going to be negative. Yeah, because you're going to have to flip one or the other, right? To get 1/3 to be powers of 3, you got to flip it. To get 2 to be a power of a half, you got to flip it, right? So they're going to be negative numbers. So let's see if we can do this without setting it equal to x and getting the bases the same. So I know it's going to be negative, and then it's just what power of 3 is 27? 3. There you go. So log base of third of 27 is -3 because 1/3 to the -3 is 27. All right, so 2 to what power is 1/16? Well, we know it's going to be negative. And now you just focus on 2 to the what power is 16? And the answer is 4. Yeah, there you go. So log base 2 of 1/16 is -4 because 2 to the -4th is 1/16. Yeah, nice. Yeah, I agree. Now, let's look at this first one here a little bit differently because you could, you still have the option of setting it equal to x. And you could do the around the world thing. So you'd get 1/3 to the x equals 27. And I just want to point this out to you, right? The get the base is the same method. You don't always have to be stuck with the base that you currently have on the left side that has the x as the exponent. You could say, wow, I don't have to write, I don't like fractions basically. So you can write 1/3 as 3 to the -1st, right? And if you write 1/3 is 3 to the -1st, now you get 3 to the -x equals 27. So that's fine. You could change that. And now you could say, oh, powers of 3 are easier. So 27, that's 3 to the 3rd. And now that you got the bases the same, you could say -x equals 3. And then it's just a matter of resolving for x, right? So you multiply both sides by -1 and you get x equals -3. So there you go. As long as the bases are the same. It could be one, the other, or it could be something totally different. All right. But let's look at this. Let's solve. Here's another warm up. Let's solve this for x. How about 8 to the x plus 1 equals 16 to the 2x minus 3. Okay, this is an exponential equation. You don't have to worry about where it came from in terms of a log, but we can solve it by getting the bases the same. By looking at it, let's see, can we write 16 as a power of 8? Yes. We can? Is 8 to the what? Second? No, that's 8 times 2. 8 to the second is 64. Can we write 8 as a power of 16 though? No, not very easily. No. So in this case, it's like, wow, I don't want to write one in terms of 8 or 16, but do they have a common base that we can write both of them in terms of? Yeah, what is it? 2, right? So we can write 8 as 2 cubed, right? And again, that's just kind of putting parentheses around the 8 and replacing it with 2 cubed. 16 is 2 to the 4th, and we still have the 2x minus 3. Now we can rely on our skills for exponents, right? Which says when we raise a power to a power, we multiply. And I would have to distribute here. So I get 3x plus 3 equals 2 to the 8x minus 12. Mission accomplished, right? I got the bases the same. Right, and again, it's preferable that you put the word so because it's coming by a theorem. But if you don't put so, I'm not going to take off. 3x plus 3 then must equal 8x minus 12. And now we're back in algebra 1, aren't we? So let's see, I'll bring the 8x over here and the 3 over there. So negative 8 plus 3 is negative 5x. Negative 12 minus 3 is negative 15. And now I divide through by negative 5. Do I flip the equal sign when I divide through by negative 5? You can, right? Because it's symmetrical. Right. Yeah. Okay. Yeah, it's not an inequality. And then you get 3, right? So there it is. X is 3. So that's kind of like a more elaborate type of get the bases the same. which is part of 4.4. 4.4, the second half of it after we learn the properties is solving exponential and log equations. And that's one of them. So when you can get the bases the same, that's the goal. If not, there's another strategy that we'll talk about maybe on Monday. All right. Questions on that? Everyone warm? Good day to be warm, right? So I realized yesterday that we skipped 2C. Did y'all realize that? Yeah, I was just kind of going crazy there. So let's go back and do 2C. We want to condense, right? We want to condense. So just to review, right? Whenever we, bless you, whenever we have a fraction, log of a fraction, we can expand it. It's going to be the positive term is the log of the numerator, and the negative term is the log of the denominator, right? And so every denominator, we said, we can skip that middle step. Every denominator gets a negative sign. Every numerator gets a positive sign, and they all get their own log. So when we're going in reverse, right, condensing, first thing we look at is, are they all logs, and are they all the same base? So yeah, there's 3 terms. They all have the same base, so that's good. So we can condense it by pulling 1 log out front. Now, if you're condensing and you have at least 1 term that's negative, here we have 3. If you have any negative terms, you know you're going to have a denominator, right? So build that shelf, right? Build the shelf. Give yourself the parentheses, the receptacle, and then build the shelf. Now, what goes on the bottom shelf? The arguments of every term that's negative. And all 3 of them are negative. And when I put them on the bottom shelf, what do I do with them? Do I add them, subtract them, multiply, or divide them? They get multiplied. Yeah, that's right. Because they're subtracted, they get multiplied in the bottom. So there's your denominator. Now, what goes in the numerator? If there's no positive terms, what goes in the numerator? A 1, you have a 1, you have a 1. Why 1? Is if there's nothing, look, before you just say 1 again, there is literally nothing in the numerator. How do we quantify nothing in math? A 0, right? So does a 0 go here? No, because if a 0 went there, 0 divided by that would wipe it out. So you're right, a 1 goes there, but why a 1? Where did the 1 come from? Where did it come from? Where did it go? Where did it come from? Cotton Eye Joe? Maybe. Magic. Well, look at over here. The identity element of addition is 0, right? The identity element of multiplication is 1. You can add 0 to anything and it doesn't change its value, right? So let me go ahead and add 0 over here. Ooh, fancy, right? Are y'all impressed? Yeah, I hope so. Well, when we multiply by clever forms of 1, like to get a common denominator, there's some insight into the form of 1 we use. Same thing here. We can add a clever form of 0. Guess what form of 0 I'm going to add here? Not that. I'm going to add the 0 that's of the form natural log of 1. What is the natural log of 1 equal to? 0. Oh, now I have another term with the natural log, and it's a positive term. So its argument gets multiplied where? In the numerator. Or you could do it this way. If you didn't know what it was and you guessed a 1, just expand it back out. Like if you were to expand it, you would have the natural log of 1 minus the natural log of 3 minus the natural log of x minus the natural log of 5x. And what is the natural log of 1? 0. Yeah, okay. So you're right. Those of you who thought 1, your intuition was good. Now we just simplify. That's the natural log of 1 over 15x squared. Boom. Okay, so that's completely condensed. All right, got closure. Now the third property that we learned, that was my favorite, right? So it turns exponentiation into multiplication. If you have an exponent on an argument, you can bring it out front as a multiplier. Or if you're condensing, if you have something out front of a log, you can bring them back up as an exponent. And that's what allowed us to kind of return over here to these problems. 2 natural log of x is the same as the natural log of x squared. Okay, sweet. Let's try these out then. Example 3, expand the natural log of 2 cubed. Well, that's going to be 3 natural log of 2, right? Yeah, piece of cake. And another version is the natural log of 2 cubed is 8, right? So the natural log of 8 is the same as 3 natural log of 2. Excellent. Now we can kind of prove why this works. I think I'm going to do that. Prove property 2 and property 3. Yeah, okay. I'll save that. But anyway, there you go. Natural log of 8. 8's a huge number, right? But 3 natural log of 2, that's manageable. All right. The natural log of x squared. Well, that's the same as 2 natural log of x. That's nice right there, because look what it did. It took a quadratic and it turned it into a linear. Oh, that's nice. That's the power of the logs. It brings it down to a linear function. All right, we can do that all day long. Look at, what about this one? What about this one? What if I had, here's a, b, we'll call this b2 again. What if I had the natural log of 3x to the 4th? Anyone in agreement? Anyone in disagreement?
Well, I see nobody disagrees.
Thank you. Yeah, no, that's not right. That's not right. Okay, here's why it's not right. The exponent of 4, it's associated with which base? X, and only x, right? What's the exponent on the 3? A 1. If you bring the 4 out front, you're assuming it's, right. Now, that would be true if this were in parentheses. Now the 4 is associated with the whole thing. So that's not going to work. But what can we do? I'll work left to right. It is a product, isn't it? So I can write it first as the natural log of 3
times the natural log of 4, or times 4 the natural log of x.
dot times. When I expand a product, it becomes a sum.
So
Each factor gets its own log, and I'm adding. And now, working straight down, in the second term, I can bring the 4 out front. There you go. Okay, so we got to be careful. Bringing exponents out front is nice, but we have to make sure that we're doing it the right way. Same thing if I were bringing the 4 back up, like if we were staring at this, if we started with this and you brought the 4 back up, you would have to be diligent and say, oh, it's going up on the entire quantity. All right. Now, what I'm hoping is, with a little practice, you can go straight from there to there. You should be able to expand it in one fell swoop. All right, let's go ahead and condense. Condense. So now I'm looking and I have 3 terms. They're all natural log. What do you notice about the coefficients of your logs? They're not all the same, 2, 2, and 4, but they're also not ones or negative ones, okay? So here's what you have to look for first. Your coefficients of your logs, and when you're condensing, must be a 1 or a negative 1, okay, to condense. Okay, so if there's something other than 1 or negative 1, like a 2, 2, and a 4, I have to get rid of those first. And how do I get rid of those? Well, we use the rule that we just did, right? Instead of bringing them out front, we can bring them back up as exponents. So that's your first step when you're condensing, right? This is the first step. So this becomes the natural log of x squared plus the natural log of 3 squared minus the natural log of y to the 4th. Now, notice what I did here. I didn't bring up the -4, did I? I left the negative there and only brought up the 4. It's a lot easier. I could bring up the -4 and call it y to the -4th, but then that's going to be like 1 over y to the 4th. So it's easier if you just leave the negative in place. Now, with the coefficients being 1 or -1, and they're all the same log, now I can pull the log out. And do I have at least one negative term? Yes, so I'm going to build the shelf. What gets multiplied on the top shelf? Your positive arguments. So x squared times 3 squared. And what gets multiplied on the bottom? Your negative argument, y to the 4th. Okay. And then once you plug all that in and you condense it, then you can simplify, you can housekeep, you can tidy the natural log of 9x squared over y to the 4th. Boom. Okay. It's not as easy to condense in one fell swoop as it is to expand in one fell swoop. Okay, let's look at letter D. Letter D, e to the 2 natural log of x. Ooh. What should I do first?
Switch around 2. So this, after we switch around the 2, would just be e to the natural full base of x squared.
Yeah, both of y'all said it. Yeah. So we're going to condense the exponent by bringing the 2 up. So it's e to the natural log of x squared. And now
we can just take out the x squared because e to the natural log of e, or e to the natural log of x of blah, e to blah.
Oh, there you go. I was waiting for the blah. E to the natural log of blah is blah, right? Because again, this is e to the log base e of blob. I call it blob, right? Is just the blob, right? B to the log base b of x is x. So yeah, e to the natural log of x squared is just x squared. E to the natural log of x squared is just x squared. What's the natural log of e to the x squared? It's also x squared, right? When you compose 2 inverse functions back to back, they undo each other. So we use this property quite a bit, but the one that we use primarily is this. The natural log of e to the x is x, and that's the same as e to the natural log of x, right? We summarized that in the previous section, right? But that's it in terms of base e. So yeah, there you go. That's just x squared. That's just x squared. Okay, let's do example 4. It says to prove properties 2 and properties 3 using the other properties. Now, when you prove something, it has to be true for all variables. So you don't choose numbers, you actually leave it with variables. And you're allowed to use any other theorems or properties other than the one you're trying to prove, right? You don't want to define a word with the word itself. So let's prove property 2 first. Property 2 is the one that says that the natural log of, I'm going to switch variables here. You can use a and b.
Property 2, wait, I'm looking at the natural log of a over b is equal to the natural log of a minus the natural log of b.
Very good. That's it. And a and b are just arbitrary variables. So I switched it to x and y just to give you exposure to different variables. Now, I think I've introduced you to proof once before. We draw a line down the middle, okay? And what that's supposed to do is it's going to keep you from interfering. You can't cross-contaminate. So in other words, if you're solving a conditional equation, you can like add 5 to both sides, right? whatever you do to one side of the equation, you can do the other. You can't do that with the proof. With the proof, you have to manipulate one side independently to make it look like the other side. And you can work on both sides, but it has to be independently. So what are some of the things you can do to an expression without changing its value? Well, you can combine like terms. You can combine like factors. You can add clever forms of 0. You can multiply by clever forms of 1. And you can actually replace something with a mathematical synonym, another identity. So which side do you want to start with? Well,
I mean, you could start with the right side and just put y to the negative first power.
oh, okay. Yeah. Yeah, you could do that.
Because that would make it for, if we then added it in the next step, it would be x over y.
Very good. So if I start on the right-hand side, this being a -1, I can bring this up as an exponent. So let's do that. This becomes the natural log of x plus the natural log of y to the negative first. And then the reason, typically we write reasons, the reason there is property 3. Yes? Everyone with me? Okay. And now I have the sum of 2 logs, so I can bring that out. And what happens with the 2 arguments? They get what applied? Multiplied in the numerator, because they're both positive terms. And this would be property 1. So again, I'm allowed to use the other properties, I just can't use property 2. And now inside, I can simplify that. What's the natural log of x times y to the negative first? It's x over y. And this would be the rule of exponents, just a generic rule of exponents. And now does the left side look like the right side except for the color change?
Yes.
Yes. So now at the bottom, you typically write QED. It's in the game, right? QED is basically the Latin way to say, hey, I did it. I did it. I did it. Yeah, we did it. Lo hicimos. Did I tell you what that stands for? Did we write that before? Quid erat demonstratum. Great word. Latin. Quid erat demonstratum. It's Latin for that which has been demonstrated. In other words, I did it. Look what I did. I proved it. I proved it. So that's starting on the right-hand side. Now, you could have started on the left-hand side. Let me show you what it would look like if you started on the left-hand side. You would say the natural log of x divided by y is the natural log of x times y to the negative first. And that would be the rule of exponents. And then I could use property 1 and say that's the natural log of x plus the natural log of y to the negative first. It's property 1. And then I can use property 3 to bring the negative out front. And now it's done. So which side is easier? I don't know. Whatever I think they're both equally as easy, but this is a proof because I did it with variables. So basically, if you would do the right side in purple, but you would do it from the bottom up, it would be the left side, right? Because when you do a proof, what you do is you create this circular sequence of logical steps. And you can actually jump in on any line and go clockwise or counterclockwise, and every line is equivalent to the one above or below. All right, let's prove property 3. Property 3 says this, the natural log of x to the nth power is n times the natural log of x. We'll draw a line down the middle. Now, for this one, we're not allowed to use property 3, right? But we can use property 1 or property 2. So I'm going to start on the left side here. What can I do on the left-hand side? Can I just bring the n out front and say done? No, because that's property 3. We're trying to prove that. So here's what I'm going to do. I'm going to, on the left-hand side, I'm going to write x to the nth power I'm going to write that as x times x times x times dot 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 times x. And how many of those do I have? N. What would be the reason? This is the definition of an exponent. The exponent tells you how many of the base you have multiplied together. Right? So now that I've gotten rid of the exponent and turned it into factors, do I know how to expand the log of a product? Yep. Property 1 tells us that. Property 1 says this becomes the natural log of x plus the natural log of x plus the natural log of x plus dot 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 plus the natural log of x. You typically need 3 of them to show the pattern, and then you put the ellipsis points, that's what it's called, to show omissions, and then you finish up. And how many of these fellas do I have? N of them, right? And that's using property 1. Now, is there an abbreviated way to add up the same term multiple times? The sign? Yeah, that's not the sign, that's the what? N is how many we have, yes? So in other words, off to the side here, 2 plus 2 plus 2 plus 2, since we have 4 of them, we have multiple 2s. We can just call that 4 times 2, right? Multiplication is abbreviated addition, multiple times. So yes, we can write this then as n times the natural log of x. And is that the same as the right side now? This would be definition of multiplication. It's the same, right? So instead of writing QED, which is a little bit stodgy, right? Another good word, stodgy. A little pretentious. What I like to do is I like to sign my name to it, kind of like a mathematical artwork, right? Corpy. Oh, is that a Corpy original? Oh yeah, it is. Yeah. Some of his early work. So feel free to do the same thing. And if you don't want to sign your name, you know, you can actually celebrate like boo. Yeah, I don't know if that's how you spell it. Booyah. Booyah. Boudin. That's different. That's rice sausage. Okay. So we've proven them now with variables. So guess what? That means that you can use those properties now with full faith and confidence. You know they're going to work. All right. Let's try example 5. I'm getting you introduced to proofs because we're going to do trig proofs later in the year. Oh, and they're so much fun. I told you about this book, right? Trigger treat. Oh, trigger treat. It's coming. Booyah. Expand in one fell swoop. Okay. We're going to learn to expand in one step. That's what that means. Okay, here we go. I got log base 7 of blob. I want to expand it. That is a gigantic blob. It's horrible. That is the mountain in front of me. I want to turn it into the smaller molehills, right? So the first thing we want to go through and do is to take inventory. How many total factors do we have? Okay, I have 1, 2, 3 factors in the top. 1, 2, 3 factors in the bottom for a total of 6 factors, right? So when I expand it, I should have 6 terms. And each term gets a log base 7, right? 3 of them are going to be positive terms. 3 of them are going to be negative terms. Yes? Okay. So when I expand it, that's not a big deal. But what I'm going to do as I write down those 6 terms with their own log is property 3 says if you have an exponent on any one of your terms, where can you put that exponent as you're writing it down? In the front. So let's do that. Let's do that. Now, I know I have a radical there in the top and a radical there in the bottom. I'm not going to take a whole line of rewriting just to get rid of the radical and write it as a fractional exponent. Because you know why? We can do that in our head as we're writing it down, right? This is a good skill, being able to expand it in one fell swoop. Here we go. We'll just go in the top from left to right, and then we'll go in the bottom from left to right. So here we go. Start over here on the left. We get log base 7 of, what's our first factor? 5. Did you say 5 or was that a squeak? It sounded like 5. Oh, you did say 5. Say it again the way you said it. Oh, it sounded like squeak. Okay. 5. Yeah, 5. There it was again. Oh, hey, hold on. Hey, Brady. I'm not there yet. But yeah, we'll see if you're right. Now, the next term is, watch this. Leave a little space. Leave a little space. It's log base 7 of x squared. But where can that 2 go on the squared? In the front. See that? You can animate it with notability. Dang. All right. And then plus, leave another little space. Log base 7 of the radicand is the quantity 2y minus 1. What would be the exponent there? 2/3, right? Because it's cube root. So that would be 2/3. But guess where the exponent can go? In front. Yeah. Now I'm no longer going to animate it like that. I'm just going to put it there, right? You get the idea. Minus, now we're in the denominator. It's just log base 7 of 2 minus log base 7 of y, and then minus what would be the exponent on the x plus 1? 1/2, and it goes in the front. 1/2 log base 7 of the quantity x plus 1. So remember, we do need parentheses around the two arguments that are multiple terms, because by default, we only accept the first term after the log to be the argument. And that's it. Not so bad, right? Y'all can handle that. That's important to be able to do that, because in calculus, we use logs quite a bit to make these gigantic expressions much more manageable. Just divide and conquer, right? And again, you can now treat each term separately. You can focus on a single term. You don't have to worry about exponents anymore. You just take care of everything and add it all together at the end. Divide and conquer, right? One step at a time. Pretty nice. Questions on that one? All right, expand this one. Now that we did it together, do the same thing. Expand it in one fell swoop. We're going to have the natural log of, how about 15 y to the 3rd times the 5th root of x squared plus 2 x plus 1 to the 9th power, well, over 14 z plus 1 times the 10th root of 11 plus 12x. Go. Oh, let's make z plus 1 to the let's make it to the, what's a good number that I have? 13. Let's make it to the third, lucky number 13 power. There we go. All right, expand it in one fell swoop. One fell swoop. Oh, yeah. Don't you? What'd you get? Oh, okay. That's what I got too. Hang on. Let me, hang on. Yeah, I got that. Okay, hang on. Let me make sure I got that too. Okay, yeah, hang on. Wait. Yeah, I got that too. Yeah, kind of. Okay, wait, one more time. Hang on. Closer? Yeah, okay. Yeah, that's exactly what I'm getting. I mean, God, yeah. You're missing some grouping symbols, though. I'll tell you that. Yeah. All right, here we go. Here we go. Let's just do the same thing. Now we got natural log. So we have 1, 2, 3, 4, 5, 6 factors again. 3 in the top, 3 in the bottom. So 3 are positive, 3 are negative. So we get the natural log of 15, done, plus 3 natural log of y, done, right? Plus, what would be the exponent when we combine the 9 and the 5th root? 9/5, good. So 9/5 comes out front. Natural log of parentheses, x squared plus dos x plus 1, right? And then minus the natural log of 14, minus 13 natural log of parentheses, z plus 1, and then minus, this is all to the first power under the radicand, but it's to the 1/10, so it's 1/10 natural log of parentheses, 11 plus 12x, close. That's it. There you go. Yeah, that was easy. So anything that has multiple terms in the argument, you need parentheses there. Huh? Something about croutons? What? 2/10. Did I miscopy something? Oh, no, that's right. Yeah. Oh, yeah, yeah. This is all, I'm sorry. Yeah, it's all to the 1. There you go. Yeah. It's to the 1th power. Thank you. Now, let's take a look at this right here. I just want to, I want to see if there's anything else we can do. Can I distribute this inside there and call it negative 1/10 natural log of 11 minus 1/10 natural log of 12x? In other words, is the natural log of a plus b equal to the natural log of a plus the natural log of b? No, very good. It's not equal. You can't distribute a log inside because, as Natalia said, the right side, natural log of a plus b, would condense to multiplication, right? That's what that is equal to. This, you're done, right? If you have an argument with multiple terms, that's it. The only thing you can do is if it had an exponent, you could bring it out front. So don't oversimplify, right? It's tempting to want to do that, but remember the log, it's a function itself. It's not like a number or a variable that you can distribute through. So don't do that. Don't do that. All right, now let's condense in multiple fell swoops. All right, it's not as easy to condense in one fell swoop. Step 1, look at your coefficients. They're all logs, but we got to get our coefficients to be 1 or -1. So I'm going to first bring these exponents back up and leave the negative in place. It's easier. So negative natural log of 2 cubed rather than positive natural log of 2 to the -3rd. The next one is going to be minus natural log of x to the 1/2 plus the natural log of the quantity 3x squared. Now notice I had parentheses around the 3x to help remind you, but we wouldn't need them around the 3x with the 2 out front. So when we bring the 2 up, though, we would have to have them there. And then the last one is sitting pretty, 2y squared. All right, now I can condense. I'm going to pull out one natural log. Do I have at least one negative term? Yeah, so build that shelf. And then your negative arguments get multiplied in the denominator. So 2 to the 3rd times x to the 1/2. And then the positive terms arguments get multiplied in the numerator. So quantity 3x squared times 2y squared. And now that I've condensed it, you do want to simplify the argument if you can. Let's see what we get. 3x quantity squared is really 9x squared. And I can then multiply the 9 times the 2 that's up there to get 18. And then, of course, it's x squared and y squared. Combine like factors. In the bottom, 2 cubed is 8. And then x to the 1/2 is the square root of x. So you can put it as the square root of x, or you can leave it as x to the 1/2. And now there's one more thing we can do, or a couple more things. Let's leave it as x to the 1/2, actually. I can simplify from high to low, remember, like we did earlier. It just so happens it's in the argument. So yeah, what is 18 divided by 8? Simplifies to? Well, what goes into them both evenly? They have a common factor of 2. So 9/4. And then I have powers of x. I can combine those. What do I do with those? Subtract. So 2 minus 1/2 is 3/2. And then y squared. So you can leave it like that. Or since we just have a number in the bottom, you can write it as 9/4 as a coefficient, x to the 3/2, y to the 2nd. There you go. And we don't need parentheses around all that because it's just one term. Fancy schmancy, right? Yeah, so we're going to do example 7 on Monday. We'll do example 8 on Monday. And let's see. Yeah, we'll finish it on Monday. So the worksheet will be due. Okay. So make sure that you're starting on the worksheet. Worksheet for 4.4 is going to be due Tuesday. Yeah, Tuesday at 9 a.m. The folder closes at 9:01 a.m. So after that, it's late. You got to email it to me. But we do have a test also on Tuesday. So I will be here Monday morning before school. I will be here Tuesday morning before school. You're always welcome to come in during advisory. We take C lunch now. So if you happen to have C lunch and you want to come in, I have 7th period conference. So if you're not doing anything in your class or you happen to have an off period, you can come hang out in the 7th period. We can talk. We get a lot of stuff done at this table. I can throw individual problems at you repetitively, troubleshoot, diagnose, and then repair. Okay. So I can't make you practice. I can only encourage you. Speaking of, I made a new meme and I laminated it and I put it up there. I'm going to start collecting my memes down the white strips here of my board. So, you know, the pointer meme where all the memes where everybody's pointing. There's so many good ones, right? So this is like the holy grail. This is all of them pointing at the same thing, and it's kind of small, but over time you'll have a chance to be up in that area of the room and you can read it. It's the golden secret to success in this class, and it's what everyone in the picture is trying to point to and remind you of. So y'all have a great weekend.